Double integrals over non-rectangular regions. Let's start by looking at an example. Notice that in this double integral, the inner integral has limits that are not constants. That means that we're integrating over a non-rectangular region. Let's go ahead and draw a picture that shows the region that we're integrating over. We start by looking at the outer integral. Since the outer integral is dx, that means we're looking at the equations x equals 1 and x equals -1. X equals 1 is a vertical line passing through 1 on the x-axis, and x equals -1 is another vertical line passing through -1 on the x-axis. Now we turn to the inner integral, which is dy. That means we're looking at the functions y equals x squared, whose graph is a parabola, and y equals -x squared, whose graph is also a parabola. It's the reflection of the first parabola in the x-axis. So here we have a picture of all the curves that are determined by the limits of the double integral. What is the region that we're integrating over? Well, we're going between the lines x equals -1 and x equals 1, and from y equals -x squared up to y equals x squared. That gives us the region that I've shaded in yellow there. We could draw a couple of arrows here to indicate how the integration is working. For any given x value between -1 and 1, we're going from the lower limit, which is y equals -x squared, to the upper limit, which is y equals x squared. Now, to actually compute this double integral is not really any different from what we did in the last lesson, with the exception that when we plug in the limits, there are going to be variables involved. But computationally, it works exactly the same way. Go ahead and take a minute and compute this double integral yourself. Pause the video, and then resume the video to check your answer with mine. So we start by doing the inner integral. Since it's dy, we get x squared y minus y squared over 2 from -x squared to x squared. When we plug in an x squared for y, we get x to the 4th minus x to the 4th over 2. And when we plug in -x squared for y, we get -x to the 4th minus x to the 4th over 2. When we perform that subtraction, we get x to the 4th plus x to the 4th, which is 2x to the 4th. And -x to the 4th over 2 minus -x to the 4th over 2 is 0. So now we just have a regular single variable calculus definite integral, the integral from -1 to 1, 2x to the 4th dx. This is just a power rule. So we get 2x to the 5th over 5 from -1 to 1. Plug in the 1, we get 2/5. Plug in the -1, we get -2/5, and 2/5 plus 2/5 is 4/5. There are two special types of regions we're going to be focusing on. The first is called a type 1 region. A type 1 region is between two vertical lines, x equals a and x equals b, and it's trapped between two functions of x, y equals g sub 1 of x and y equals g sub 2 of x. To compute a double integral over this type of a region, we change it to an iterated integral of the form dy dx, where the outer limits are x equals a and x equals b, and the inner limits are y equals g sub 1 of x and y equals g sub 2 of x. Similarly, we have a type 2 region. A type 2 region is trapped between horizontal lines, y equals c and y equals d, and goes from left to right from the function x equals h1 of y to the function x equals h sub 2 of y. To compute this type of double integral, we change it to an iterated integral, dx dy, where the outer limits are y equals c and y equals d, and the inner limits are x equals h1 of y and x equals h2 of y. Let's try some examples. Go ahead and pause the video, try these examples yourself, and then resume the video to check your answers with mine. The first one, evaluate the double integral over the region R, e to the x plus 3y dA, over the region bounded by the graphs of y equals 1, y equals 2, y equals x, and y equals -x plus 5. The first thing we always want to do is to sketch the region. It's very hard to write down what the limits of integration are without having a sketch in front of us. So let's go ahead and do that. Y equals 1 is this horizontal line, and y equals 2 is this horizontal line. Let's draw y equals x. That's just a line passing through the origin with slope 1, or 1 over 1. And y equals negative x plus 5 has a y-intercept of 5 and a slope of negative 1, or negative 1 over 1. So we see that this yellow region here is the region that we're integrating over. This works best as a type 2 region because we're trapped between two horizontal lines. That being the case, we want to solve each of the given equations for x. So y equals x is the same as x equals y, not much to do there. For the second one, y equals negative x plus 5, I'll subtract 5 to get y minus 5 equals negative x. And multiplying through by negative 1, we get x equals negative y plus 5, or equivalently, x is 5 minus y. It's always nice to draw a little arrow, especially when you're first starting out, to see how the integration is going. We're going from left to right, so we're going from the function x equals y to the function x equals 5 minus y. Since this is a type 2 region, the double integral is going to be dx dy. The outer limits are given by the two horizontal lines, y equals 1 and y equals 2, and the inner limits are given by the two functions of y. X equals y is the leftmost one, and x equals 5 minus y is the rightmost one. So the lower limit is y, the upper limit is 5 minus y. Now to compute this is pretty straightforward. We first do the inner integral, e to the x plus 3y. Since we're integrating with respect to x, we just get e to the x plus 3y. Technically, there's a little substitution there, u equals x plus 3y, but du is just dx because the derivative of 3y is 0 with respect to x. It's being treated as a constant. So we have e to the x plus 3y from y to 5 minus y. When we plug in the 5 minus y, we get e to the 5 minus y plus 3y, which is e to the 5 plus 2y. And when we plug in the y, we get e to the y plus 3y, which is e to the 4y. We now have to do the inner integral. So that becomes 1/2 e to the 5 plus 2y. Notice there's a little substitution there. U equals 5 plus 2y. So du is 2 dy. So we need the 1/2 to make up for that extra 2. Similarly, for the second half there, e to the 4y, that becomes 1/4 e to the 4y. Again, if we let u equal 4y, then du is 4 dy, so we need the 1/4 to cancel out that 4. All right, and this is going from 1 to 2. So when we plug in the upper limit 2, we get 1/2 e to the 5 plus 4, or e to the 9th, minus 1/4 e to the 4 times 2, which is e to the 8th. And then when we plug in the 1, we get 1/2 e to the 5 plus 2, or e to the 7th, and 1/4 e to the 4 times 1, or 1/4 e to the 4th. So the final answer is 1/2 e to the 9th minus 1/4 e to the 8th. All of that minus 1/2 e to the 7th minus 1/4 e to the 4th. Next one, evaluate the double integral over the region R, xy dA, over the region enclosed between y equals 1/2 x, y equals root x equals 2, and x equals 4. Once again, we want to draw a picture first. Y equals 1/2 x is a line passing through the origin and with a slope of 1 over 2. So from the origin, if we move up 1 over 2, we could get another point and then draw the line. Y equals root x looks like this. I just drew the part of y equals root x until it hits the line. Notice that the point 0, 0 is on both y equals 1/2 x and y equals root x. And the point 4, 2 is on both of those curves because 1/2 of 4 is 2 and the square root of 4 is 2. X equals 2 is this vertical line and x equals 4 is this vertical line. So the region we're interested in is this yellow region here. Since we're trapped between two vertical lines, this would work best as a type 1 region. So when we do the integral, we're going to be going from the lower curve, which is y equals 1/2 x, to the upper curve, which is y equals root x. Writing the integral as an iterated integral, x is going from 2 to 4 between those two vertical lines. And for the inner part, y is going from the lower curve, which is 1/2 x, to the upper curve, y equals the square root of x. Again, it's dy dx because we're doing it as a type 1 region. So we're doing the dy integral first, the inner one. That becomes y squared over 2. The x just stays where it is because it's being treated as constant. We're going from 1/2 x to root x. When we plug in the root x, we get x over 2. And when we plug in the 1/2 x, we get 1/4 x squared. So simplifying this, we have x times x over 2 is 1/2 x squared, and x times 1/8 x squared is 1/8 x cubed. So we're left with 1/2 x squared minus 1/8 x cubed as the integrand, and this is now just a regular definite integral from single variable calculus. We do a couple of power rules. We get 1/2 x cubed over 3, or 1/6 x cubed, and then 1/8 x to the 4th over 4, or 132 x to the 4. And it's going from 2 to 4, plugging in the 4, we get 1/6 4 cubed, which is 64, minus 1 over 32, 4 to the 4th, which is 256, minus 1/6 2 cubed, or 1/6 of 8, minus 1 over 32 times 2 to the 4th, or 16. That all comes out to 11/6. You can check that computation yourself. Next, find the volume of the tetrahedron bounded by the coordinate planes and the plane z equals 4 minus 4x minus 2y. Once again, let's draw a picture of the situation here. Since we're being asked for a volume, it's nice to have a three-dimensional picture. So what I'm going to do is I'm going to plot the three intercepts of this plane so that we could get a nice picture of the plane as it passes through the first octant. So if I set x and y equal to 0, I get z equal to 4. So I'll label the z-axis with a 4 there. If I set x and z equal to 0, then I get 0 equals 4 minus 2y, or 2y equals 4, so y is 2. So I'll label the y-axis with a 2 there. And if I set y and z equal to 0, then I get 0 equals 4 minus 4x, so that x is equal to 1. So I'll label the x-axis with a 1 there. And then I'll go ahead and draw line segments from one intercept to the next for each of the three pairs of intercepts, from the x-intercept to the y-intercept, from the y-intercept to the z-intercept, and from the z-intercept back to the x-intercept. Let's also now draw the region. The region is that triangle in the xy plane. Notice that the x-intercept of that triangle is at 1 and the y-intercept is at 2. So we do have to rotate the picture a little bit to draw it in the xy plane. You can either see geometrically what the equation of this line is by putting it in slope-intercept form, or you can just set z equal to 0 in the original equation, which is what I did here, and then go ahead and solve for y. If we bring the 2y over to the left, we get 2y equals 4 minus 4x. Divide by 2 to get y equals 2 minus 2x. This one could be done either as a type 1 or a type 2 region. By default, I'll usually do type 1 if there's no reason not to. We're going to take the double integral over the region R of 4 minus 4x minus 2y dA. Remember that the main geometric interpretation of a double integral is to compute a volume, the volume that's below a surface and above a region. The surface that we're below here is z equals 4 minus 4x minus 2y, and the region that we're above is the region drawn in the xy plane on the lower right of the slide here. We're going to do this as a type 1 region, so when we write it as an iterated integral, x is going from 0 to 1, and y is going from the lower curve, which is just the x-axis, or y equals 0, to the upper curve, which is that line, y equals 2 minus 2x. This integral is very straightforward, but pretty tedious. It's just a bunch of power rules, but there's a lot of extra algebra that you need to do, multiplying things out and such. So I'm going to leave it like this and let you finish this one on your own. Next one. Evaluate the integral from 0 to 2, the integral from x squared to 4, x e to the y squared dy dx. At first, it might seem like we got away without having to draw the picture because we already have the limits of integration. But unfortunately, when you try to do this integral, you basically have a constant times e to the y squared. And since we're integrating dy, you want to integrate e to the y squared dy. This is a classic example of an integral that cannot be expressed in terms of an elementary function. So what we're going to have to do is we're going to have to change the order of integration. So we're going to use the limits given to draw the picture of the region, and then we're going to change from a type 1 to a type 2 region so that we get a double integral that we could do. So let's start by drawing the picture. Since the outer limits are dx, the region is trapped between x equals 0 and x equals 2. Now for the inner limits, we have y equals x squared, and it's going up to y equals 4. So the region is this shaded part in yellow. Notice when I drew the picture, I did it as a type 1 region. So we're thinking of it as between 0 and 2 on the x-axis, and going from the lower curve, which is y equals x squared, to the upper curve, which is y equals 4. We now want to rewrite the integral using it as a type 2 region. So we're now going to think about it going from left to right instead. So starting with the original integral written as a type 1 region, we're going to change it to an integral as a type 2 region by changing from dy dx to dx dy. And we see that y is going from the horizontal line y equals 0 to the horizontal line y equals 4. And x is going from x equals 0 to the right until we hit y equals x squared, which we have to rewrite in terms of x as x equals the square root of y. Notice it's the positive square root because it's to the right of the y-axis. Doing the inner integral first, dx, x just becomes x squared over 2, and the rest just sits there as a constant. And now we're going to plug in the limits. When we replace x by root y, we get root y squared, which just becomes y. So we have 1/2 y e to the y squared, and the integral is going from 0 to 4. Notice what happened. We generated an extra factor of y, which we can use in a simple substitution problem. By changing the order of integration, we went from an integral that we couldn't do to an integral that's pretty straightforward. So if we let u equal y squared, then we have du is 2y dy. So we put in the 2 next to the y. And to balance that out, we multiply by 1/2, and I'll put that outside of the integral. So we have 1/4 the integral from 0 to 16, e to the u du. So we replaced y squared by u. We replaced 2y dy by du. And when y is 0, u is 0 squared, so it's also 0. And when y is 4, u is 4 squared, which is 16. So integrating that is straightforward. We get 1/4 e to the u from 0 to 16, which is 1/4 e to the 16 minus 1. So we replace u by 16 to get e to the 16th, and we replace u by 0 to get e to the 0, which is 1. So we wind up with 1/4 e to the 16th minus 1. Last one, find the area of the region R enclosed between y equals 4x and y equals x squared. So I just want to point out here that even though geometrically double integrals represent volumes, we can actually use double integrals to find areas of regions also. Basically, if you don't put anything inside of the integral, meaning the integrand is 1, then you will be computing an area. Now, technically speaking, you're computing the volume of a solid whose base is given by the region and whose height is 1. But when you compute the volume of a solid of height 1, you get the same numerical answer as the area of the region. Technically speaking, the units would be different. Volume is given in cubic units and area in square units, but the numerical answer is the same. So let's draw a picture of this situation. Here we have y equals 4x and y equals x squared. And this is the region that we want the area of, enclosed between them. So we need to find the points of intersection here. One is clearly the origin, but to get that other one, we're going to set x squared equal to 4x, bringing everything to one side of the equation. We have x squared minus 4x equals 0. Factoring, we have x times x minus 4 is 0. So we see that x equals 0 and x equals 4. So plugging 0 into either of those equations gives us y equals 0. So 0, 0 is one of the points of intersection, as we already knew. And plugging a 4 into either of those equations for x, we get y equals 16. So 4, 16 is the other point of intersection. So as I said, we could compute the area of a region simply by taking the double integral over the region dA. In other words, there's a hidden 1 inside that integrand. If we don't write anything inside of the integrand geometrically, we can think of it as computing an area. So let's do this as a type 1 region. So x is going from 0 to 4. Just look at the two x coordinates of the points. And y is going from the lower curve, which is y equals x squared, to the upper curve, which is y equals 4x. So when we integrate this dy, we just get y from x squared to 4x. Plugging in, we get 4x minus x squared. We are now down to a regular single variable definite integral. Just some power rules. 4x becomes 4x squared over 2, or 2x squared. X squared becomes x cubed over 3, and we're going from 0 to 4. So 4 squared is 16, so we get 2 times 16. 4 cubed is 64, so we get minus 64 over 3. When we plug in the 0, we just get 0. So this comes out to 32 minus 64 thirds. 3 times 32 is 96, so getting a common denominator, we have 96 thirds minus 64 thirds, which is 32 thirds.